Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is oscilloscopes. Our objective is to take a quick look at the oscilloscope, a tool used to not only measure, but also graphically depict a time-variant voltage waveform on a screen. If you recall in the AC voltmeter lecture, available at the Big Bad Tech channel, we used a DMM to measure the RMS voltage value, the frequency and period of a time-variant sinusoidal voltage signal. Recall the DMM displayed a numerical result consistent with our expectations. However, never went to the trouble of drawing out the AC waveform on a display. Today, we'll examine a tool called the oscilloscope that, in addition to displaying specific numerical measurements, can also depict a graphical representation of the AC waveform under inspection. For the purposes of today's lecture, we'll be making use of the Tektronix TBS 1032B digital oscilloscope. This in no way is meant to be neither an exhaustive review of this tool nor an endorsement of this particular manufacturer or model. I only wish to present the functions of interest on a representative example so the viewer can gain some practical exposure to these functions and interpret the manner in which results are displayed. Since the oscilloscope is historically the single most misused, maltreated, and misunderstood piece of equipment in the lab, we need to establish some basic ground rules up front. First, no one calls an oscilloscope an oscilloscope. All the cool kids call them oscopes or just scopes. Second, remember the rules for the family gun cabinet? Don't touch anything unless you're given specific authorization to do so. The same rules apply here. Don't touch nothing on your oscope unless I tell you you can touch it. This practical advice prevents you from both metaphorically and literally shooting yourself in the face. Finally, and most importantly, your oscope is not broken, so don't tell me it's broken. I've yet to witness a genuinely broken oscope, but I have on frequent occasions witnessed oscopes being used improperly. The intention of today's lecture is to teach you how to use the oscope properly, but as I'm trying to politely emphasize, you've got to do exactly what I say and absolutely nothing else. Like giving a toddler a handgun and hoping for the best, letting the discovery process unfold naturally with an oscilloscope and a beginner user is a bad idea under full sail. My intent is to guide you along a very specific and defined path. Your job is to simply stay on the path. Bottom line up front, an oscope is exactly like a voltmeter, only it displays a picture of voltage. An oscope takes repetitive samples of voltage, then draws the result on a display that one can zoom in or out on, shift up or down, left or right, and with pretty minimum effort perform some basic measurement, comparison, or mathematical operations on. The oscope is a powerful, sophisticated tool. However, the scope of today's activities is to limit ourselves to only the most basic, essential, and effective functions of the oscope and leave the rest for later. To make sure you don't wander off the path and get lost, remember what I told you. Don't touch nothing unless I tell you you can touch it. Let's first look at the display area. Most oscopes, including the Tektronix TBS 1032B, feature a screen with 8 vertical divisions and 10 horizontal divisions. The vertical divisions are in units of volts. The horizontal divisions are in units of time. The oscope screen can therefore be thought of as a means of plotting voltage as a function of time, where the vertical y-axis is volts and the horizontal x-axis is time. Note the horizontal axis typically runs right through the middle of the screen. However, one can independently position this up or down, as we'll learn in a moment. Given time-variant voltage forms can swap polarity many times a second at speeds beyond human perception, the oscope's ability to capture these waveforms allows a human operator to visualize this phenomenon. Additionally, an operator can zoom in or out to the required scale and make a desired measurement on the waveform under inspection by adjusting the value of each vertical or horizontal division. Before exploring an application of this feature, let's perform a brief tour of the rest of the oscope. I'd like to draw your attention to 4 critical areas: the vertical group, the horizontal group, the triggering section, and the array of operations buttons along the top. The vertical group consists of 2 channels, channel 1 in yellow on the left and channel 2 in blue on the right. This oscope is dual channel, meaning it can simultaneously display 2 voltage waveforms on a single horizontal time axis. These channels are part of the vertical group, since the vertical or y-axis is in units of volts. One can adjust the vertical volts per division scale for each channel independently using the scaling knob directly above each channel input. The second group to the right is the horizontal group, which is just the horizontal or x-axis time scale. One can adjust the horizontal seconds per division scale for both channels simultaneously using the large knob on the bottom of the horizontal group. The third group all the way to the right is the triggering section, which we'll examine later. The fourth group at the top is all the buttons one uses to measure, set up, save, recall, or otherwise operate the oscope. Within this group, the multi-purpose knob in the upper left is the principal means one uses to select menu options displayed on the screen. It's somewhat tricky to use in that an operator rotates the knob to navigate within a menu and then pushes the same knob to select the option. We'll examine menu navigation in a moment. In summary, an oscope consists of a screen with volts on the vertical y-axis and time on the horizontal x-axis. Elements within the vertical group are used to adjust volts per division for each channel, and the horizontal group is used to adjust seconds per division for both channels. The triggering group and the function buttons. You are now hereby authorized to touch only the vertical scaling knob for channel 1, the vertical scaling knob for channel 2, the horizontal scaling knob, and nothing else. Application of these features necessitates a bit of an example for purposes of comparison. Consider a pulsed DC waveform with the following characteristics. It consists of regular pulses of 5 volts and 0 volts entirely on the positive side of the voltage axis. Alternatively, one could view this as pulsed AC waveform with a 5 volt peak-to-peak value going between positive 2.5 volts and negative 2.5 volts, including a positive 2.5 volt DC offset, thus shifting it entirely to the positive side, but this just complicates the issue. The easiest way to think of this for now is just alternating pulses of 5 volts and 0 volts. This pulsed waveform can be said to have a 50% duty cycle, and that there are equal spans of full on and full off. The time on is 500 microseconds long, as is the off time. The waveform then repeats itself. This pulsed waveform can therefore be said to have a 500 microsecond plus 500 microsecond, or 1 millisecond period. A period of 1 millisecond corresponds to a frequency of 1 over 1 millisecond, or 1 kilohertz. For the remainder of this lecture, we're going to use this waveform and nothing else, so you may as well get used to it. In summary, 5 volt pulses at 50% duty cycle with a period of 1 millisecond corresponding to a frequency of 1 kilohertz. Ordinarily, a function generator could be used to create such a waveform. However, the Tektronix TBS 1032B conveniently features a test point on the lower right-hand side that continuously generates this exact waveform. This test point can be used for initial setup of the oscope and demonstration of basic oscope scaling functions. Before we view this test form in the oscope, let's briefly examine an Otoscope probe. First and foremost, a probe features a grabber and an alligator clip. And unless the probe is fixed, a slider that selects whether the probe attenuates the signal or not, and by how much. Let's talk about the attenuation feature first. Most probes feature a slider that toggles between 1x and 10x attenuation. Attenuation is the act of reducing something. An attenuation of 1x means the value isn't attenuated and the probe will deliver 1 volt to the oscope for every 1 volt differential experienced at the grabber. In contrast, an attenuation of 10x means the value is attenuated 10 times and the probe will deliver only 1/10 of 1 volt or 100 millivolts to the oscope for every 1 volt experienced by the grabber. Does 10 times attenuation mean division by 10? Yes it does. And in my personal opinion, the 10 times label is a severe mischaracterization of what the setting actually does. For our example waveform with 5 volt peak values, this is well inside the measurement range of the Tektronix TBS 1032B, so attenuation is unnecessary. If, however, we were to measure some larger voltage, we might need to attenuate it. For our purposes, let's leave the probe at 1x or no attenuation. We'll examine how this oscope deals with attenuated signals in a moment. Let's return our attention to the grabber and alligator clips. These are the two measurement points, similar to the probes in a voltmeter, between which a voltage differential is measured. Easy, right? Not really. The alligator clip, unless explicitly identified as an oscope featuring isolation, is always directly connected to ground. This means that the simple act of touching something with the alligator clip ground references it. which, as we'll learn in later applications, may be a total deal breaker. For now, just consider the grabber as equivalent of the red lead of a voltmeter and the alligator clip as equivalent to the black, the caveat being that this black lead is always directly connected to ground. The test point conveniently features both the test signal output and a ground reference for test purposes. Before we display this test waveform on the screen, we need to adjust the oscilloscope to the proper vertical and horizontal sensitivity settings. Let's use a vertical sensitivity of 5 volts per division, meaning each division has a magnitude of 5 volts. Given our test waveform conveniently has a magnitude of 5 volts, we should expect each pulse to be 1 full division high. Since we're using only channel 1, we only need to concern ourselves with channel 1's vertical sensitivity. Spin the channel 1 vertical scaling knob until you see the vertical sensitivity on the screen at 5 volts per division. Let's now scale the horizontal axis. Let's use a horizontal sensitivity of 1 millisecond per division, meaning each horizontal division has a magnitude of 1 millisecond. Given our test waveform conveniently has a period of 1 millisecond, we should expect 1 complete cycle to occur inside 1 full horizontal division. Spin the horizontal scaling knob until you see the timescale at 1 millisecond per division. When we hook our probe to the test point, our waveform might look something like this. Note the waveform peaks out 1 division above the center line. Given each vertical division is intended to be equal to 5 volts, it can be demonstrated that 1 division at 5 volts per division equals 5 volts, as one might expect. It's a unit conversion. Given each horizontal division is intended to be equal to 1 millisecond, note a complete on and off covers 1 full division. Additionally, given a 50% duty cycle, note the on portion is roughly half a division, as is the off. 0.5 divisions at 1 millisecond per division results in these equal on and off time spans being 500 microseconds long, as we'd expect. If we wanted to zoom in on this waveform, we could readjust the vertical sensitivity on channel 1 to 2 volts per division. Note the pulses appear to increase in magnitude, however this is an illusion only since each vertical division is now worth only 2 volts per division. Given this increased level of vertical magnification of the same 5 volt pulses, each pulse takes up 2.5 divisions at 2 volts per division rather than 1 division at 5 volts per division as previously. Absolutely nothing about the test waveform has changed, only we've zoomed in a little bit. This holds true for horizontal sensitivity as well. If we change the horizontal sensitivity to 250 microseconds per division, note the 1 millisecond period seems comparatively wider than previously. However, and this is important, it's still the same waveform. It still features regular 0 to 5 volt pulses every 1 millisecond. This is the utility of an oscilloscope. You're never confined to just one scale, and you can always zoom in and out on each axis independently as you see fit. This is to suggest that an oscilloscope can be a tool of casual observation as well as an instrument of fine detailed inspection. Consider the vertical and horizontal sensitivity respectively set to 5 millivolts per division and 10 nanoseconds per division. At such an astronomically zoomed in scale, note we only see an extreme close-up of the rising edge, the equivalent of an ant looking up at a sequoia disappearing into the sky. Theoretically, a perfect pulse should exhibit an instantaneous transition from 0 to 5 volts. However, the oscilloscope at such an exaggerated magnification is showing us this clearly isn't the truth. Note this pulse exhibits a noticeable slope transition as well as transient electrical noise. And as great as this feature is, this is also a principal source of trouble for those individuals new to oscilloscopes. If you're too zoomed in or too zoomed out, you can often get a distorted view of your target, so much so that you miss it entirely. To prevent this from happening, know what you're getting into beforehand and make sure you select an appropriate scale in advance. Do the calculations first. Before we move on, take a quick look at these 3 plots. They're all the same test waveform with 5 volt pulses at 50% duty cycle at a frequency of 1 kHz, only they're being shown at different scales. The first one has a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 10 milliseconds per division. Note it shows a huge number of cycles at this level of backed out horizontal sensitivity and it's hard to get a clear picture of an individual pulse in the larger crowd. The second one has a vertical sensitivity of 5 volts per division and a horizontal sensitivity of 100 microseconds per division. Note the waveform seems pretty squat and barely fits one cycle on the screen. If our first attempt was equivalent of taking a picture of a crowd of people, this would be equivalent to taking an extreme close-up of one of the people in the crowd. Finally, the third one has a vertical sensitivity of 2 volts per division and a horizontal sensitivity of 250 microseconds per division. Note the Oscilloscope shows a decent snapshot of a couple full cycles. This would be equivalent to getting a well-focused portrait of a couple people inside the crowd. Importantly, despite the exaggerated differences, all these pictures are of the same waveform, only they've been zoomed in or out, sometimes to a comical degree, to make a point. The point being the waveform never changes, only the level of magnification does. They're all showing 5 volt pulses at 1 kHz. Under different levels of magnification, the waveform under inspection can and will assume bizarre forms.